Hi everybody, welcome to another video. I think this video is gonna be a bit more chill than some of my other content. There's music in the background, and that music is probably copyrighted, so that's probably not good for my future YouTube career. But you know, life is short. Life is short. We are all only for a finite number of days on this earth. So why not get as many copyright strikes as we can while there's still time, you know? So that's what we're doing today. Also, the title of this video, it's either not very provocative or potentially very provocative. I haven't really decided yet how I want to title this video. So if I'm feeling less provocative, I'll title it "Why You Should Care About Foundations in Math." I think that's not very provocative. I think, you know, you can make a fair case for why we should get a little philosophical every once in a while. Nothing really wrong with that. But then maybe like a more provocative way to title this video would be something like there is still a foundational crisis in mathematics, which I believe is true. You know, I believe it's true. I wholeheartedly believe it's true, but maybe not everyone believes equally strongly that we have some sort of philosophical crisis in mathematics. From my point of view, it really is like kind of an overarching, like really big crisis almost, because there are lots of people doing math nowadays, and let's just say some of that math that people do, it's very abstract, and something that I have come to appreciate as I have done more and more math. I haven't done a lot of math. I'm still young. I am still beginning my mathematical career, but I think sometimes too much abstraction can actually can maybe hinder you. Like, not only does it make your theory harder to understand for other people, but like, I think more importantly, you can actually run into some philosophical quandaries. You know, is it, you know, are you really doing the right kind of math? You know, so this is very controversial potentially, but we don't have to take it so seriously. You know, if you're a mathematician, I think this topic has potential to for you to not really enjoy this discussion that we're gonna have. But if you're not a mathematician, if you're just maybe interested in math for fun, and you're just interested to hear different takes, then maybe you'll find this interesting. So welcome to my bedroom. Just kidding. This is not my bedroom. This is just, yeah, I rented this apartment just for the video. Yeah. No, actually, in real life, I'm actually laying on my carpet, not even on my bed. So truly, nothing is real. Nothing is real anymore. It's all just acting. Yeah. But anyway, before yapping further, I think I should probably give a quick overview of what I'm going to be talking about, because for some people, what I'm going to be talking about isn't that interesting, and if it's not that interesting to you, then I don't want to waste your time any more than necessary. I've already wasted a bit of your time. Sorry about that. So I will talk a little bit about the historical development of geometry, actually, because I think geometry, the study of geometry was actually, I mean, not only was it like historically important for mathematics, but I think that was actually the thing that really sparked questions about the foundations of mathematics, I would say, from what I understand. So we're gonna get to that. Basically, like Euclid's parallel postulate. Maybe you've heard of that, the whole thing. So that thing, but there's actually an interesting thing that came out of that, and some of these things that I'm gonna be talking about maybe aren't as appreciated by most mathematicians as they should be, in my opinion, right? So this is all just my opinion, right? People can different mathematicians can have different opinions. Sorry, dying. So my opinion is not the only possible opinion out there, but obviously it's my channel, so I will broadcast my opinions, and nobody can stop me. Anyway, so we're gonna be talking a little bit about what happened in geometry, right? But then there's like basically what comes out of geometry, really, in geometry of all places, is model theory. And so it basically we overhaul our axiomatic method, right? So like I'm sure like you're watching a video about math, right? So you probably know what axioms are. You've probably heard the term axiom, at least used in some context. But there's actually a good chance, even if you're like a math student or even like a math researcher, maybe not if you're a math researcher, but like there's a good chance that you don't actually appreciate what an axiom really is, you know, because mathematicians and philosophers have not always agreed on what an axiom is supposed to be, what it really is, right? And we're gonna get to that. We're gonna get to what it was. I mean, I think probably your intuitive idea of what an axiom is probably the way the word was used historically, as something that that is like so obvious that we can assume it to be true, you know? But in modern math, the way we do things is maybe a bit more subtle. Maybe a bit more subtle, because like maybe I won't get to it yet. But just because we know something to be true, just because we know a collection of statements about something, that doesn't necessarily mean we understand what we're talking about, right? Like, just because we know certain properties of our little quirky little construction or our quirky little mathematical thingamabob, that doesn't mean we know that doesn't mean we know what's going on. You know, we can know for sure these axioms, right? And we can still have no idea what's going on. All right, okay, and that's like, and this was like a huge step forward in mathematics. It really changed everything. Okay, and then finally, I'm going to be talking a little bit about the constructible universe, I believe it's called. So it's like basically, you know, mathematicians, we or I should say they love set theory. I actually don't love set theory myself, but yeah, mathematicians in general, they love set theory. And so they have this question, you know, you've probably all heard Russell's paradox before. They have this problem of, you know, what should we count as a set, right? And that's not an easy question to answer. But one answer to that question is the constructible universe. And it was Kurt Gödel who came up with that, maybe, but I don't remember. I don't remember. So we're gonna talk a little bit about that. One way to construct sets. And then we're gonna talk a little, and that's gonna be the controversial part of the video. We're gonna talk a little bit about why it's a bit strange. You know, like, why do we have these sets? And do we understand what these sets are? Like, really, deep down in our hearts. You know, do we know what's going on, right? And I would like to maybe convince you that deep down in our hearts, we don't know what's going on. We're lost. We're confused. And yeah, finally, maybe I should suggest that there's maybe hope. There's maybe a different way of doing mathematics that might be better. I don't know. I'm not an expert, right? I'm hoping that one day, I'm just sharing my own experience, right? So I'm hoping that one day, maybe I will do some research in that direction, and maybe it'll turn out to be good somehow. Hopefully. But who knows, right? So there is like potentially an alternative way to do things, maybe. And not everyone is gonna agree with it, but hey, this is my channel, so yeah. And if you know the name Professor Wildberger, NJ Wildberger, then and you absolutely despise him, right? Then maybe maybe click off this video, because you might despise me as well. I'll try to be reasonable. I'll try to be cool, you know? I won't, like, preach my agenda too hard. But yeah, I'm a pretty unorthodox person when it comes to the philosophy of mathematics. So some of these things that I will be presenting will be a bit unhinged, you might say. Not everything. I will tell you the parts that are unconventional, because other stuff that I will talk about is actually very insightful, even for the quote unquote average mathematician who doesn't mind all these crazy sets that we're gonna be constructing. But yeah, that's what I thought I would talk about today. So welcome to my bedroom again. Strap in, and so forth. Yeah, for maximum immersion, you know, I recommend, actually, if you're watching this on your phone, take your phone to ground level and lay on your carpet. So that's like maximum immersion, because I'm laying on my carpet right now, so we can be like laying on the carpet together, or on your bed. That is, because yeah, of course I wouldn't be laying on my carpet. Obviously I'm laying on my bed, you know. This is you see my bed right here? This is my bed. Anyway, yeah, also, if you're watching this on your phone, there's a good chance that some of this text that I'll be writing, you won't actually be able to read, because it's gonna be very small on a phone screen. So sorry about that. Yeah, I'm still perfecting my craft, so, yeah. Well, but we'll see. I'll probably be yapping quite a lot more than writing, so maybe it's all good, right? Okay, so I promised to start out with geometry, right? That's the promise that I made. So I'm gonna keep my promise, because I keep promises. I am very trustworthy. Right. So, so there was this person called Euclid. I think we've all heard of them. Actually, I'm gonna erase all of this. It's gone. It's gone. We'll never see it again. Unless you rewind the video, then you'll see it again. That's the power of YouTube. Okay. So, Euclid. Euclid. So he was like an ancient mathematician. I don't know when he lived, because I'm not a history nerd. I just like the math. But he was a dude, and among other things, probably, he really enjoyed geometry. And he wanted to axiomatize geometry, right? So back in his day, you know, they would have like people, you know, drawing drawing a circle, and then drawing, this circle has a center. Then you draw its diameter, and then you draw this inscribed triangle. And then through crazy geometric deduction, which we're not gonna go into because I don't remember what they did. They deduced that this right here is a right triangle. Yeah. So that this is what people would call Thales' theorem, I think, or something like that. So they would like draw diagrams and make geometric deductions, right? But they started thinking, like, is it really rigorous mathematics to draw a diagram? And based on the diagram, you look at it and you're like, well, of course it goes like that. That's beautiful. That's good. And then they have their little proof square. I mean, I don't think they had their proof squares back then, but they're like, this is proven now that I have this diagram written down. No, Euclid didn't really like that approach. He wanted geometry to feel less subjective. He didn't want someone to accidentally draw the wrong line, and then it would like prove some statement that shouldn't be provable. So Euclid kind of started the what some people refer to as the axiomatic method. So that is like in contrast with the scientific method. So in mathematics, we like axioms. And to Euclid, what he called axioms, he basically meant things that he thought were just obvious, right? So one of Euclid's axioms was that if you have 2 points, this point here and this point here, then you can draw a line going through them like this, and you can do that. And Euclid said that the fact that you can always do this for any 2 points, that's an axiom because it's so obvious. And then anytime he would oh, I don't know what my avatar is doing. Yeah, so Euclid said that this is so obvious, that let's have it as an axiom, and then I can always refer to this obvious result. And Euclid would have a few of these, like, what he considered obvious results, and then, based on them, he would prove things that maybe aren't so obvious from the axioms alone, right? And Euclid thought this was beautiful, right? Because he basically built complexity out of simplicity, right? Simple little axioms, but then you use deduction on top of those axioms, and suddenly you have this like beautiful forest of mathematical truth. It's like, I don't know if this is a needless analogy, but this is my art channel. I'm an artistic person, so I can make any analogies I want. So Euclid, he planted little seeds, and trees grew out of those seeds, and or are they called, in Minecraft they have tree seeds. Trees grow. But then once you have those trees, what he noticed was that, I don't know if this is a good analogy, the trees would grow branches, and those branches would form a canopy, and that canopy felt like a forest. So maybe that's one way to think about the beauty that Euclid did. From very simple little trees came something that no one would have expected, right? But to Euclid, these things, they were just evident truths. And if you have evident truths and you deduce something from them, then everything that you deduce must also evidently be true. So that's how Euclid thought that he made geometry rigorous. Well, Euclid was great, but unfortunately, Euclid, his axioms weren't perfect. There were some details missing, right? So later came David Hilbert. Who's like considered one of the top G's of mathematics, right? David Hilbert. And this top dog, David Hilbert, I don't know why I'm squaring, putting David Hilbert in a square, but I don't know. I can do whatever I want, because Hilbert is cool, you know. So what did Hilbert do? Hilbert basically kind of patched up Euclid's geometry axioms, because there were some problems with those. But he also, like, while doing that, I guess I don't know, like, the exact historical details, but I think he paved the way for what modern mathematicians know as model theory. Okay, so that's a big word. I'm gonna write it down. Model theory. So, what's a model? Obviously, like, maybe some of you are used to the word model in the context of we're modeling the real world. But in mathematical logic, it actually has a bit of a different definition, or like a pretty precise definition. Precise, I don't know, but maybe. Anyway, yeah. So model theory. What's a model? Well, basically, what Hilbert realized is that, okay, so let's, you know, so there are some axioms, right? So there's axiom 1, axiom 2, axiom 3, then also some definitions that make it easier to write your axioms and so on. You have like a list of axioms, let's say n axioms, right? Now, what Hilbert realized was that, so, oh my god, how do I even explain this? So, one pretty infamous axiom by Euclid that did not feel like the other axioms was Euclid's parallel postulate. So, Euclid's parallel postulate, like, loosely speaking, it's kind of that that parallel lines exist, right? Loosely speaking, very, very loosely speaking. So for any given line over here, I can basically find a point such that a line going through that point, it never intersects my original line. So that if I can always do that, then the parallel postulate is satisfied, or something. Now, Euclid thought that, you know, this should be provable from the other self-evident truths, right? Because I don't know if this is self-evident, you know? Like, in order to make it self-evident, you kind of, I mean, what would you even do? Like, because lines can keep going on forever, but you can't draw a line going on forever in our finite little realm here. So what do? How can we be sure that these lines never intersect, right? How do we know? And David Hilbert came along. Well, I don't know if it was him who actually like came up with this, but something along these lines. Somebody came along and they said, what if the lines don't intersect? Sorry, what if the lines do intersect? Or don't, or do, or don't, like whatever, right? And that's kind of how we get into model theory. So basically, people discovered that you can have Euclidean geometry, where the parallel postulate holds, Euclidean geometry, or alternatively, you can also have hyperbolic geometry.
hyperbolic geometry. And I'm not going to go into detail as to what hyperbolic geometry is, partly because I don't know. But basically the upshot here is that we had these axioms, right? And we realized that there's not just like one thing, one construction, Euclidean geometry, that satisfies our axioms. There's also another thing, hyperbolic geometry, that also satisfies our axioms, right? And this was kind of how like hyperbolic geometry was discovered, I believe. So mathematicians tried to find little constructions that would satisfy all the, quote-unquote obvious truths. But they realized that there are actually different things that satisfy these, quote-unquote obvious truths, right? And this was the beginning of model theory, and this was huge for the philosophy of mathematics, right? And, I don't know, but honestly, I don't know why this took them so long to figure out, from my point of view. To me, it feels kind of obvious that, just because you have certain conditions, that doesn't mean that it uniquely identifies what you're talking about. You know what I mean? You would think, right, that, if I say that I have a vegetable, and it's yellow, and it's round, kind of, then, that could be either a lemon or some other fruit or vegetable. I don't, but you know what I mean? You see my point? I'm not good with vegetables, I'm sorry. We can have these conditions or these axioms that we think obviously hold for our, let's say our lemon, right? So, okay, this is actually a good way to put it. So here's a lemon, right? Where should I draw this? I really want to draw this lemon because I really want to, y'all get the point probably, but I really want to emphasize this because I'm really proud of this point. So, we can start listing out things that are obviously true about our lemon, right? It's yellow, it's kind of round, you can eat it, stuff like that. But how can we be sure that those properties ever truly define the lemon, right? Because Euclid thought that if he just lists the right properties, you're going to have your lemon narrowed down. Because how else would you define a lemon, right? How else would you do it other than by listing out its most important properties? But the crazy thing is that oftentimes you can actually have different objects that fulfill your criteria that you thought were central to only this one lemon, right? And that's how hyperbolic geometry was born, right? People thought, these axioms, this is only for Euclidean geometry. But then they realized that we can actually have this thing that is almost like Euclidean geometry, but just without the parallel postulate or whatever. And then suddenly we can have this other type of geometry that is ever so slightly different, but still useful, right? And people started understanding that, because, what Euclid was trying to do, right? Again, I'm maybe repeating myself. Euclid was trying to define geometry by taking its most important properties and saying, this is what geometry is. But what Euclid didn't realize was that you can never be sure that you've narrowed down exactly what you want to talk about by just listing out properties. And honestly, that's okay. That's the big thing. Mathematicians weren't crushed by this. They were actually empowered by this, right? Because what does this mean for the mathematician, right? Because now, right, now, if I have something that satisfies Euclid's or Hilbert's axioms, I know that whatever the hell I'm doing must also have these properties that they've proved for me. So I don't need to prove all those things again, right? And this is like, if you don't know what like groups and fields are, then don't feel discouraged. But that's like the same thing. You know, we don't know what a group or a field is in practice. But if someone comes along and satisfies our axioms, then we've already done a lot of work for them in terms of what structure their little construction has. So that's what this is all about, you know? That's what model theory is all about. You find different constructions that satisfy the same set of axioms, right? And those constructions are called models, right? Yeah. So there are different flavors of geometry, and there's like a set of axioms that they both satisfy, but they're still different. And yeah, that's pretty cool. Okay? So in modern mathematics, there's basically two ways. I love this music. I just hope it's not too loud. I don't think it's too loud. There's basically two ways to do math, essentially. Honestly, I'm gonna erase this. So pause the video if you still want to look at it. I don't think you do. I think you've seen it. You've already seen it. All right. So there's two ways to do mathematics. You can either A, find the perfect model. So maybe that's like the perfect like set of little elements that you work with, and it just happens to model reality perfectly as you want it, and that you're content with that. So find the perfect model, right? Or alternatively, you can study axioms. Study the consequences of axioms. And most mathematicians, they do the second thing. They don't really care about this first thing at all. Isn't that, yeah. I mean, you would like naively, or maybe not naively, but instinctively, you would think that, oh, you know, I want to find this perfect model, right? And once I find the perfect model, I have mathematics all solved, right? Or not all solved, but you have like a foundation to do mathematics on, because models are like, those are the actual things, quote unquote, that like actually exist. You know what I mean? Like, yeah, like that model is like, that's something real. Axioms are just statements that can cover a whole bunch of different models. But if you choose a model, then that's what the modern mathematician would think of as being something that you actually have, that you can touch almost. I mean, you can't touch math, but you know what I mean? Like, it's like, it's there in a way, right? But most people actually just take axioms and study what those axioms entail, right? So like a very notorious example of axioms is actually the ZF and perhaps even C axioms, right? So ZF is Zermelo-Fraenkel, or whatever, I probably butchered that pronunciation, and C is for the axiom of choice. And these are basically axioms for set theory, right? And now, usually, if you ask a mathematician, what is a set, or what is a natural number, they're always gonna default to saying, oh, it's just ZFC axioms. ZFC axioms, those define your natural numbers, right? Because those define sets, and natural numbers are sets. We actually, in another previous video of mine, I actually showed you the von Neumann ordinals, or actually not all of them, only the finite ones. In this video, we might actually cover the rest of them, maybe. I don't know. Anyway, so a lot of mathematicians, they will say that, oh, ZFC, that defines the natural numbers, because that defines sets. But really, philosophically speaking, they don't define anything. Like, they describe certain types of vegetables, if you like. But what is the vegetable? Which vegetable do we choose? They don't tell you. So, like, if a mathematician tells you that they know what the natural numbers are because they are somehow determined by ZFC, then the mathematician, in a certain sense, is lying, right? I mean, obviously, like, a mathematician who knows a little bit more about model theory and this type of stuff will just say, well, like, truth is, I don't care what the underlying model is. I don't care what a set is exactly. As long as it satisfies these axioms, it's all good. Like, we're chilling, like, at the end of the day, like, we don't like money because it's, like, a specific kind of money. Like, it doesn't matter whether it's money on our bank account or cash on hand, right? Because, like, those are, like, physically speaking, those are very different entities. Like, physical cash versus digital numbers in my bank account, right? Those are different things. But, like, functionally, they do everything I want money to do. I can use that to buy stuff, right? So the mathematician will say, I don't care what my set really is. All I care is that I can use it to buy stuff. I can use it to construct the natural numbers. So that makes me happy. So I don't care about your little philosophy. And maybe that's fair. Maybe that's fair. Maybe that's the way it goes. But I love philosophy. I'm crazy. I'm crazy like that. I want to get to the bottom of things, right? So we have different models of ZFC, right? Now, what do those models look like? Yeah. I think a lot of people expect them to be somehow, like, very, I don't know, like, rigorously defined or something, and they kind of are, but I don't know. I guess I'll let you be the judge of it. So, right now, maybe, let's think a little bit about the constructible universe. So what is this thing? This is the constructible universe. I'm just gonna say uni because I'm lazy. Constructible universe. Oops, I smacked my keyboard against a physical object in my room, breaking the immersion. Sorry about that. Constructible universe L. So it's called L for some reason, right? And it's like we build it in steps, right? So kind of the way it goes is that we have the first step is like the empty set, right? And I guess, like, we don't really tell you what a set is. We just tell you that we have sets and we have this, like, set is in another set, like relation. And I actually haven't looked into this, like, in tremendous detail, but I don't know. I don't know how maybe it's rigorous. I guess it is rigorous. Yeah. So we have sets, right? And we have this element is an element of relation, whatever. And we have an empty set. Gosh darn it. I wonder if I should actually move a little bit. Okay. So, yeah, the empty set. And then at the end, right, after all these steps, right, this constructible universe L, it's going to be the union. It's going to be the big freaking union of all of these L's, right? And I don't want to say that I would be a natural number, because oh boy, it's going to be bigger than that. It's going to be crazy. Yeah. So what is the point of this constructible universe? Well, it's going to be L is going to contain every set that we could ever want to work with, right? So that's why we call it a universe, because like the universe contains every atom that we would ever want to work with. I mean, I guess we don't really have any other choice because we're stuck in this universe with these little atoms that we interact with. You know how it is, science. So similarly in mathematics, we want to like construct our own universe of little atoms that might interact, and we can study how they interact. The problem is that our universe is going to contain a lot of atoms, like a lot of them, like way more than our current one, because our current one probably contains a finite number of them, like the physical universe. But this one is going to contain an infinite number of them, and not only an infinite number, but actually an unfathomable number, like to the point where it feels like fiction. And if you ask me, to me it kind of is like I don't really believe that this is like a good model, and I don't believe that the ZF axioms are good axioms, because they imply that any model of ZF, if I recall correctly, must be infinite. So that's like, why did we choose these axioms? But anyway, so we're constructing every atom, every set that we could possibly want to work with, right? So that we start out with the empty set, but it's gonna get out of hand pretty soon. So the second one, so basically the way that this goes down, right, is that you always take subsets of the previous one, right? But you only take those subsets which are constructible in a certain sense. And when I say constructible, I basically mean that there's a first order formula, right? So I should say constructible equals first order formula. And when I say first order formula, I basically mean like kind of the logical symbols that you would expect, but then also these quantifiers, like this existential quantifier. You've probably seen this around. So this is, there exists an element, so you can use that, and you can also use for all y, for instance. So these are quantifiers, and you're allowed to use these. And these are kind of fucked up. These are kind of fucked up because they bring infinity into the picture, right? Like there are unsolved problems in mathematics, lots of them. For instance, I believe the Goldbach conjecture is one unsolved problem in number theory. I don't remember what the statement of Goldbach conjecture is, because I'm not a nerd, I'm just a dog. But we have plenty of statements that we don't know how to prove and will probably never prove, right? If Goldbach conjecture gets proven, we can just find another one. It's really not a problem, right? So, and we can formulate these very difficult statements in first order logic. So first order logic is like strong. Like in general, it is very difficult to determine whether a statement in first order logic is true or not, right? And that is in stark contrast with propositional logic, because then I believe there is actually a general algorithm for determining whether a statement is true or not. Maybe you can even just like it's kind of like a brute force thing. I don't know. Anyways, there's so we have like different flavors of logic that allow you to do different things, right? And for some reason, when we construct our universe of all these sets, we use like the most messed up sort of rules available to make the most messed up sets. I mean, obviously we want to do that, right? Because we want this thing, we want it to have like a lot of elements, right? We don't want to just like wish for an element but then it wouldn't be there in our universe. That would be really sad, you know? Like imagine like you try okay, this is a stupid analogy. Imagine you wish every night before you go to bed, you wish for your perfect loving partner to be somewhere out there in the world. But then the world said, sorry, that's not part of my universe. Right? So in this constructible universe, it is actually going to be so vast that that whatever encoding you use for the atoms in your body, this thing is going to contain the encoding of you and me and anybody else, just the perfect human being or the perfect dog. It's gonna contain that thing inside this set, and like conceivably it exists in our universe. So is it, I mean, like I'm kind of saying this like it sounds like a joke, but it's like not even a joke because it's true. Like this thing that we're building up, it's gonna be so fucking crazy, it's gonna be so vast that literally, if you encode my entire human body using ones and zeros up to crazy precision, this set is going to contain that encoding. Okay? That's wild to me. And it kind of makes you think, like, like, does this exist anywhere? Is this real? Are we just dreaming this stuff up? I think we are. But honestly, it's fun to dream. So let's keep dreaming together. Mathematicians are great dreamers. So yeah, let's keep dreaming. So okay. All right. Let me double check that my recording is still going. It is going, and it's going 47 minutes strong. So it's gonna be a banger. Anyway, so let's keep going. So we can use first order formulas, and they can contain quantifiers, so they can be really crazy. So for instance, Goldbach conjecture, if you Google that right now, I don't remember what the statement of that is, but basically any conjecture you can think of, the twin prime conjecture, or whatever, you can write it in prepositional logic, most likely. Like this this language of prepositional logic is strong. Or sorry, first order logic. It's sometimes called prepositional logic, I think. But yeah. I think it's kind of confusing because there's also propositional logic, which is different from prepositional logic. But yeah. Propositional logic is okay. First order logic is like kind of not, kind of crazy. I don't want to say it's not okay, but it's kind of crazy. Okay. But like, this is the language that mathematicians use on the regular. Like, if you open up a calculus textbook or any type of textbook, you know, I want to emphasize this, like, you know, I'm going to stand up. This is so crazy. This is how serious I am. I'm standing up. Ooh, wow, you can see me stand up. Wow, okay, cool. So if you open a calculus textbook, you see something like, for every epsilon, there exists a delta. And then you have these like conditions where if the value of the function blah 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 is less than epsilon, or sorry, actually it's the other way around. God, I'm stupid. Let me just undo a little bit. So if the, and I'm sorry, like you all know how continuity works. Well, there's, if your x's are restricted by this little delta that you have, then from there you're actually gonna the values of the function are gonna be whatever less than epsilon, whatever. Who cares, right? Oh, that's not even visible on the thing on the recording. Okay, it doesn't matter, right? It doesn't matter. Point that I'm trying to make is that these things, these slimy fuckers, sorry for using foul language. This is no longer a family-friendly stream. Sorry, not stream, video. Getting my words mixed up. But this could be a stream, maybe, one day. I could, like the stream that I did yesterday, actually, but I don't know when this video is gonna go live, but I did a stream, and it was just my face cam, right? So it was kind of lame, me trying to read a textbook. But I can make a VR chat stream, streaming in VR chat, and I could even have my friends in there too. So yeah, I could become a VR chat streamer. Could be crazy. Anyway, so drop a comment down below if you'd like to see that. Anyway, so what am I saying, right? So these things are everywhere. These nasty things. So it's like, yeah, we're cooking up something magical, but we're not really breaking any conventions of mathematics. This is the way mathematics is done. But if you think this is crazy, then yeah, it is pretty crazy. I don't know how I feel about it. Okay, but anyway, let's keep cooking, right? Let's keep cooking with what we've got. Eventually, I'm actually gonna run out of music, but I can just play it again. It doesn't matter. It's an hour-long loop over there. God, I'm so excited. I'm getting so excited about math. Wow, okay. Yeah. Okay. So, let's collect ourselves. So, basically, we take all the subsets of the previous collection of sets. Such that, but not every subset necessarily. We only take those which we can form using a first-order formula. And that formula can contain elements from the previous set, but ultimately, it's going to be like a formula that determines whether or not the new element is going to belong to our new set, right? So maybe that didn't make sense, but basically, for instance here, I mean, for the first, for these finite ones, finite ordinals, I should say. So the 0, 1, 2, 3, 4, 5, those are called finite ordinals because they're finite. They make sense. They are made up of a finite number of sets. By the way, if you remember from the other video, the way we define 0, 1, 2, 3 set theoretically, right, is that 0 is the empty set, then oh my god, then 1, so 0 is the empty set, 1 is does this show? Yeah, it's fine. 1 is every contains every subset of the previous one. So every subset of the empty set is just the empty set, like that. And then 2, oh my god, I'm running out of space. Then 2 is going to be every subset of the previous one. So what is that going to be? It's going to be certainly the empty set or the set containing the empty set. So that would be the full set. And so forth. And this would be every subset of this and so on. Okay? So those are the von Neumann ordinals, right? So that's one way to so if you accept that a set exists, we can define the natural numbers by convention using sets. For example, like this. But that's just an arbitrary convention, right? That's just someone that Neumann was Neumann was let's do this. Why not? Let's do it, right? And it's just a convention, so it's not that deep. But yeah, these are finite ordinals because they always contain a finite number of sets. But the crazy thing about sets, right, is that they don't always have to contain a finite number of elements. Well, if you ask other mathematicians, if you ask me, this is all crazy talk, but but yeah, generally mathematicians will be okay with infinite sets, right? Okay. So, and then they will actually be called transfinite ordinals, right? And if you do induction on those, it's called transfinite induction. Isn't that wonderful? Okay. I'm getting way too excited. So what is this L1 thing, right? So we're constructing our constructible universe, and we're going to take the union of all these sets. And our first set is the empty set, and our second set is actually going to be every constructible subset from the previous one. Now it turns out that for these finite ordinals, these constructible sets are always going to be just every single subset. So that's going to be the same. It's going to coincide perfectly with the von Neumann ordinals, right? So this is going to be every single subset of this. So it's either the empty set or the whole set, which is the set containing the empty set. And I guess maybe for clarity, let me see. For clarity, let's also draw a third one, and hopefully it's not going to be impossible to read. Might be impossible to read, but whatever. The third one is going to be, again, every single subset. So it's either the empty set or it's the set containing the empty set, or it's the set containing the empty set, or it's the set containing both of those. So it's the empty set and the set containing the empty set. Yeah. And you'll notice that these actually increase in powers of 2, right? So that's like a general result. That's maybe good for y'all to know, you know? So this is 1 element, this is 2 elements, this is 4 elements. So let me see, 1, 2, 3, 4. And the next one would have 8, and then 16, and 32, and so forth, right? So the number of subsets of a given set, that always increases in powers of 2. And maybe you should think about why that is. Maybe pause the video, think about it. But I'm going to spoil it for you. So the reason is that the way that you can think about constructing a subset is for every set in the previous set, you just ask, you know, do we include this set in the new set or not, right? So depending on if we include the first one, that splits the world of possibilities in 2. And then depending on whether we include the second one as well, that again splits those in 2, right? So the world, or the like tree of possibilities, that always splits in 2. So that's where the power of 2 comes from. Okay, cool. Yeah, so basically, yeah. And I claimed, right? I claimed that all these subsets are what I call constructible. So that means there's a first order formula that describes them. And in fact, I think there is actually a propositional formula that describes them. So we don't even need these quantifiers or anything. So for instance, we can just define. Well, we might need to define equality of 2 sets in terms of these quantifiers, maybe. I'm not an expert. I haven't really thought about this. But, you know, you can just have a formula that, like, for this set, for instance, the set that contains only the empty set, so this one, you can just have a formula that says, if your set contains the empty set, but it doesn't contain anything else, right? Because we're allowed to use these previous, like, elements, nothing else, only the empty set. Then include that in your set. Or what am I saying? Yeah, or like if the element is the empty set, include it, otherwise don't include it. So that is going to include the empty set, right? And that would be like your first order formula that defines this. Okay, yeah, this is this is already like so unbearable now that the music is gone. Oh, but the music loops without me having to do anything. So that's the magic of VR chat in my bedroom. So welcome to my bedroom. Okay. Yeah. Maybe this world, I mean, I just found this world randomly. I actually Googled like worlds with marker and I found this world. But maybe this could canonically be my bedroom. My bedroom is just this cool in virtual reality. In real life, it's horrible. Yeah. Okay. Cool. So, what am I saying? So, yeah. All of these sets we have a first order formula for them. I don't know if I should give like an example of that formula, like for clarity, you know? So the formula can contain like a what we call like a free variable, right? And the free variable is what you plug into the formula, right? So let's call the free variable y, right? So our formula, it could be like and we are, again, like, we're allowed to use every single element in this L2 set, right? So we're allowed to use the empty set, and we're allowed to use the like empty set inside a set, like element, right? So our formula for the formula that corresponds to the set containing the empty set, right, to this set, the formula that corresponds to it could be y equals the empty set and y doesn't equal the set containing the empty set. So now this propositional formula defines this subset because only for the empty set does it return true, and then it gets included, and otherwise it doesn't get included. Actually, I messed up, right? Because this right here, this was not an element of L2, so I cheated. Plus, I don't want to do that. So basically what I meant to say is like without these. So like the set containing the empty set. That's what I meant to say. So now this empty set and this set containing the empty set, they are both in here. And then this propositional formula for L3 would define this set containing the empty set. I don't know if you know what I'm talking about. Maybe this is crazy talk. But yeah. Yeah. And obviously some people, because I don't remember how this stuff works, some people might object to me using an equal sign here. But if you object to me using an equal sign, then obviously we have these quantifiers, so we can just get around that by saying something like, for all x, you know, so we can say that two sets y and z are equal if for every x, like x in x and y implies x and z, and also x and z implies x and y. And then not equal to would just be the negation of that, right? So we can get around equality by and just use the is a member of relation, right? And this is basically what I mean. And then it works. And yeah, so if you don't, and this right here, it corresponds to the statement that y is equal to z. And then if we apply this logic over here, it's gonna work, right? So yeah. Yeah, this is maybe confusing, but anyway, yeah, so we can form these, but this is the part that even I don't really have a problem with, right? This is all good, right? But here's where it gets crazy. Yeah, oh my god, I'm getting exhausted. You know, math is exhausting. I'm actually gonna be late from this sauna event that I should go to. But yeah, I'm finished. So I do the sauna thing, if you've ever heard of that. It's like a hot room where hot men go to get hot and steamy. Okay, sorry about that. That was a very unnecessary description. Yeah. I need to keep going. I need to finish this video. Okay. Admitting that I'm getting exhausted doing math is probably not the best thing to admit when doing a chill math video, because then you are probably also gonna hate the rest of this. But sometimes it's good to admit that you're getting a bit exhausted, you know, and you're just watching this video, right? So you can take a break. You know, you can pause this video right now and go browse TikTok or whatever it is that kids do these days. And then you can come back or not come back. But anyway, I'm going to keep going. If you want to push through with me, then welcome. You're welcome to push through. So, this is all fine and dandy, right? So, basically, let me actually erase all of this probably. So we have these sets, right? We have these sets which it's gone. We have these sets which correspond to the von Neumann ordinals, right? So we have L1, which is the empty, or L0, which is the empty set, and so on, right? Now that goes on, all fine and dandy, all the way until stuff gets transfinite. That's when stuff gets crazy. And we're gonna actually meet the idea of a limiting ordinal, right? That's cool. That's cool. So, so at some point, you know, we say that there is an ordinal called omega. And omega is the union of all the finite ordinals, right? So omega is the union, and this is going to be really cursed, right? But remember that these are sets. We can define these using the von Neumann convention as sets. So we have the union of 0 and 1 and 2 and 3 and 4 and so forth, right? And that, my friends, is the von Neumann, sorry, what is it? This is the first transfinite ordinal. And I think it might be called Aleph null, but I'm not sure. Honestly, I don't remember, so I don't know what it's called, but we're just gonna call it omega, right? It's the first transfinite ordinal, right? I remember when I was little, I watched a video by Vsauce where he explained these like transfinite ordinals, so like bigger and smaller infinities basically. And I remember I watched it. I thought it was so cool, right? I didn't understand it. I was like, how could this possibly, who comes up with this shit? And it's funny because now I'm an adult and I can genuinely, I still think like, who comes up with this shit? I mean, it's not as crazy as it seems. Like it kind of makes sense, but then it also like, infinity is just, it's a weird thing, right? So this is an infinite union, right? And we just assume that we're allowed to do that because why not, right? We're mathematicians, we can dream stuff up. That's what we do. Yeah, I don't necessarily support this, but this is how it's defined. So yeah, so we have an infinite union of all the finite ordinals, and that's the first transfinite ordinal. So I guess like, it would be like a set containing the empty set, and then the set containing the empty set, and then blah blah blah, but like it would go on forever, right? Because there's an infinite number of these subsets, right? Okay, cool. I should become a yoga instructor, like we need a yoga break in here. It's too much math, it really is too much math. But anyway, this is like I should title this video ADHD dog does math,
because that's what it feels like. I feel like, I mean, I don't have diagnosed ADHD, but I probably have ADHD and just learned to cope because I love math so much that I keep coming back to it. But I am very easily distracted. Maybe it's the microplastics in my brain. Maybe it's the same microplastics that turned me into a furry, you know. I don't know. Okay, so let's keep going. But it's so chill. The music is so chill. Do you really want to keep going? Or do you just want to chill here? Okay, let's keep going. This is the eternal struggle of getting stuff done in my life. But this is a YouTube channel. I have an audience. I have an audience to entertain, so let's keep going. Or not entertain, I mean educate. This is educational content. Yes, so we have our first transfinite ordinal. This is actually called a limiting ordinal. Okay? Now, these are sets, right? Oh, there's like a little thing flying in front of me. Ooh, it's cool. Anyway, for some reason, I actually don't remember how this works. But for some reason, we can define like omega plus 1. And I don't remember how that worked. I don't remember how that is like how you should think of that, how that's constructed. I genuinely don't remember. Oh, maybe it's just like, right, because this is a set, right? So I'm not sure, but maybe it's like you take this set and just add the 1 or the 0 element to it and then keep going somehow. Anyway, you can conceive that there's probably like a way, like you have an infinite set here and then you start adding stuff to it and whatever, right? Like we can define this omega plus 1, and we can define, oh, where did my pen go? We can define omega plus 2 and so forth. And at some point we will actually get omega plus omega, right? Which I think some people write omega squared, if I remember correctly, right? Okay, so how's the time? It's over an hour, and yeah. I don't know. I might not like even see my friends today, which is crazy, because I'm too busy being a YouTuber. But that's okay, honestly. I'm chilling. I don't mind. Maybe I'll skip it. Maybe I will. Yeah. So it's also really cold. Warm because it's summer. So yeah, I don't know if I should take my shirt off. Oh, this is getting feisty. This is getting feisty in here. Honestly, I will take my shirt off because it is very, very hot. And obviously this will not affect your viewing experience, because I'm just a dog, you know, I'm naked anyways. But anyway, give me a second. Okay, I have taken off my shirt, and you can have your little fantasies in the comments about like how that's like hot or something, but literally I'm just doing it because it's hot, like literally hot in my room. Yeah. Okay, cool. Let's keep going. So, yeah. Okay. Oh, this is exhausting. I'm just kidding. I love doing math. So, omega plus 1, omega plus 2, omega plus omega. Some people write that is omega squared, and so on, and this keeps going. And this omega right here, and also this omega squared, these are called limiting ordinals. Now, intuitively, why are they called limiting ordinals? Well, whenever you have, like, let's say you have, like, 110, that ordinal, right?
That's a finite ordinal. But when you have omega, that contains an infinite number of elements. So it's like a limiting case of what you approach as you keep listing out numbers, kind of. Or that's the way set theorists think about it, right? And similarly here, if you have omega plus 1, omega plus 2, omega plus 3, and so on,
you just keep going, you just keep counting up, you know? But then at some point, you approach this value
called omega plus omega, right? Kind of, in a sense, right? Now, what's the definition, right? Because it's like, we approach this set. That's not formal, rigorous mathematics, right?
So what is the definition? So the definition is actually that, that there exists no smaller ordinal such that there would be wiggle room, right? Yeah, something like that. So for instance,
so the thing you have to understand is that these things, like, are ordered, right? So, like, 1 is smaller than 2, and that's smaller than 3, and so on. So they form this very nice ordering. They're probably well ordered or something like that. So well ordered generally means that you have a total order, which means a whole bunch of things. I'm not gonna get into that. I actually went into that in another video, right? So yeah, and then the well ordered on top of being a total order means that for any subset you have a smallest element, something like that. Yeah. Okay. Anyways, so here's the deal. If we have, let's say, 100, right? Well, we can find 99, and nothing goes between 99 and 100, right? So that means that 100 is not a limiting ordinal. But if we take omega, well, it doesn't matter what we put in here. We can put a number as large as we like 10 to the power of 10. But we will always have numbers in between, or ordinals in between. We will always have 10 to the power of 10 plus 1, for instance, right? But with omega, all right, okay, so omega is a limiting ordinal. So this is a limiting ordinal. Because there's like no element that precedes it, like comes before it, you know? And it's the same with omega plus omega, right? So if we have omega plus omega, so what is that? What would be the one smaller than that? Well, it doesn't exist because, again, like, it would have to be like omega plus something, but there's nothing that you can put in there that would not leave wiggle room between them. So that's why omega plus omega is also a limiting ordinal. Okay?
So that's it. Those are transfinite ordinals and limiting ordinals.
And, okay, back to this constructible universe, right? So, for finite ordinals, right, and remember, at the end we take the union, so we take everything we happen to build along the way, right? And, for finite ordinals, it's very simple. It's the von Neumann ordinals. But for infinite ordinals, what do we do? Actually, for infinite ordinals, so it depends on whether it's a limiting ordinal or not. So if it's not a limiting ordinal, then we can like, so let's say it's like, let's say it's omega plus 1, right? Well, in that case, we just do whatever we just described, like we take all the constructible subsets. Maybe I should write, I should write that. So constructible subsets of L omega, right? But if we have L omega, well, here's the thing, like, there's no previous element, right? So we need to do something a little spicy, right? So I think we take, in that case, we take the constructible subsets of, instead of, the previous element, we take the union of every Li where I is less than omega, right? Something like that. And that way we can, like, define this Newman constructible universe, right? Okay. So, long story short, right? We find this universe, right? So what are some elements that are a part of this universe, right? Maybe I should erase this, right? So the long story short is that L, because it's the union of all of those, L contains everything right? I mean, maybe not everything, but like the natural numbers, and then also like more stuff. So like a lot of stuff. I guess not like everything, but like like a lot of stuff, right? And what's an example of something that belongs to L? Well, like there's so much, like, and I'm probably not going to be able to make this point very well, but for instance, we could have the way we could make a subset is like take every element where, if we can formulate Goldbach conjecture in first order logic, right? And if it's true, right? So we take Goldbach and then like y equals the empty set, or not Goldbach. Wait, how does this work? I think this works, yeah. Or Goldbach and if Goldbach is true, then we want the empty set, but if Goldbach is not true, then we want the set containing the empty set. So now, so this set, right, it's a part of L, right? And depending on whether it's the empty set or the set containing the empty set, depending on that, it tells us whether Goldbach's conjecture is true, right? Kind of. This is just kind of stupid. You know what I mean? Like, he can do all kinds of these stupid sets, right? And they are like a part of your universe. Now, obviously, like in practice, it doesn't really matter whether Goldbach's conjecture is true or not, because we already know that L is going to contain this empty set and this set containing the empty set, so who cares, right? And that's fair. That's a fair point. But this is just to like illustrate the analogy that we can really define any kind of set we desire. And that's strange, like we could define, I don't know, I mean, we can define like rational numbers and stuff, and then we could like define, I mean, there's probably like some crazy binary string that we can like, I mean, there's everything. You can define like everything. It's crazy. And I don't know if that's good. I don't know if that's good. But anyway, that's pretty crazy. So that's the constructible universe. Yeah, it has a lot of elements. I guess to end off now. Okay. I actually forgot to talk to you a little bit about why we care, right? So this is a model of ZFC. And I'm not going to show you why it's a model of ZFC, because frankly, I don't know and I don't care. But it's a model of ZFC, meaning it satisfies the axioms of ZFC, right? Including the axiom of choice. I don't know why I even put it in parentheses. This set satisfies the axiom of choice, which already maybe tells you that it's kind of a crazy set, because the axiom of choice is crazy. Anyway, yeah, so it's a model of ZFC, but you can have different models too. And the crazy thing about this model, because this model is just crazy, well, this model satisfies the continuum hypothesis, right? We often abbreviate that to CH in the business. And the continuum hypothesis basically says that there's like no wiggle room between like the smallest transfinite ordinal, so like the natural numbers basically, and the real numbers. So in this model, we can construct the real numbers so that there is no wiggle room, or something like that. And when I say wiggle room, I mean like cardinality and whatever. But I haven't looked into any of that stuff, so sorry. I'm not a nerd. I'm not a set theorist or a model theorist. Yeah. So this model happens to satisfy the continuum hypothesis, but we could have another model of ZFC that is like maybe something similar or something kind of different, and it could be that it doesn't satisfy the continuum hypothesis, right? So it turns out that truly, when mathematicians say that, you know, your sets are just whatever that satisfies our ZFC axioms, well, that doesn't mean anything, because there could be a way to define your sets such that they satisfy the continuum hypothesis, or another way to define them such that they don't. So basically, we don't know what sets are, and who's to decide which model is the best model for mathematics, right? And I think as long as the models are infinite, I don't think that question is going to reach an answer or like a consensus. But what's the solution then? What's the solution? I think the solution is to consider finite models. And this is actually not possible with ZFC, right? Because if I recall correctly, any model of ZFC is necessarily infinite. Or maybe it's trivial or something. Yeah. ZFC is bad, in my opinion. So in finite models are cool. Yeah. And quickly, maybe I'll mention Professor Wildberger's work here. So he's a really cool guy. He's like, I think he's like originally from Canada, but he teaches or works in Australia. So Professor, and this is like, you know, people hate this guy, right? I like him, but like some people will hate me just for mentioning his name. But you made it till the end of the video, so presumably maybe you're not gonna hate me for having different opinions on math. So Professor Wildberger, he has a pretty funny name. One of these days, I would love to actually meet him in real life. That would be great. If you pay like an absurd amount of money to his Patreon, he actually offers to like meet you if you visit Sydney. But I don't have absurd amounts of money, so Wildberger, if you're watching this, drop a comment. I like you a lot, and I'd love to meet you. So, yeah, I'm a young aspiring mathematician, and I will honor your work. I will expand on it somehow. Because so Wildberger, Mr. Wildberger, Professor Wildberger, has written a book called Rational Trigonometry, where he basically does he essentially, in the context of what we've talked about today, he basically gives us a model of geometry in terms of rational numbers, kind of. And that's very nice, right? Because rational numbers are nice. So the reason that rational numbers are nice is that it's just two finite ordinals. That's it. And finite things are very nice. So two finite ordinals. That's what a rational number is. A over B. Two finite things. And if you contrast that with the real numbers, right? Those are not very nice, right? Because a real number, one way to define it, is as a Cauchy sequence of rational numbers. So you have your first rational number, and then your second rational number, and so forth. Like that. And that's an infinite amount of rational numbers, so it's kind of crazy because it's infinite, but rational numbers themselves are very nice because they're finite. So basically Professor Wildberger developed geometry and especially trigonometry for these rational numbers, and it works out surprisingly well. And instead of angles, because those are often real numbers, instead of angles, you just use a different measure that is very similar to an angle, right? So you have two lines, and you kind of want to measure how displaced, or what's the word? How spread. I think Wildberger calls it the spread of two lines. So how spread out they are. And basically you can just take some point here and take a look at what's the ratio by which it gets scaled down when you project it. And that's a rational number, and that's a rational measure of how spread out two lines are. And this gives a very nice, potentially nice model of geometry, and yeah, hyperbolic geometry back in the day, that revolutionized everything, right? Because it encouraged, or it motivated the theory of relativity, I think. So that uses crazy geometrical notions, which were inspired by this sort of philosophical inquiry. Similarly, Wildberger's work is also motivated by this philosophical desire to avoid infinities in the real numbers. And honestly, what he came up with, his book, Rational Trigonometry, Divine Proportions, it's a very good book. I highly recommend it. I think you're going to enjoy it, especially after this video. Unless you hate everything I said at the end here, in which case I'm sorry. Yeah. I mean, at the end of the day, who knows? Who knows what's right or what we should do? I don't want to make this personal. Because there are people working in analytic number theory, and they need their integrals and infinities and whatever. And I don't want to disrespect anyone who does any type of mathematics, because at the end of the day, we're just doing art, and it's cool. You know what I mean? I don't think it has to be that deep. I don't think it has to fulfill my personal ideals of what I think is beautiful, because I think beauty is in the eye of the beholder, right? But if you've never thought about this before, if you've never thought about what a model is and why infinite models contain a lot of crazy sets and stuff, then maybe now you've thought about it. I think and just quickly, so what is the argument? Well, I think it boils down to computability. That's one thing. So if you have sine of, let's say you have sine of 3, right? Well, sine is defined as an infinite series, and sine of 3 is going to be some never-ending decimal that you're never going to be able to compute, right? So computability is something that motivates rational trigonometry, for instance, because then everything is just computable, like on pen and paper, which is nice. You don't need like machines that give you some decimal expansion that you then have to truncate, because that's kind of lame. But then the other thing actually comes from physics, right? So in physics, the things that we have, I mean, certainly, okay, so the biggest like argument or the biggest criticism is like, okay, but how are you going to do analysis without the real numbers, right? And we're going to get to that at the very end, I think. But hopefully it's possible, right? Not many people have even tried it. That's the main thing. I think if people just try to make it work, I think we'll cook something, right? But yeah, that's a fair point. But when we look at many other areas of physics, like quantum physics in particular, there's really not a lot of analysis that goes into quantum physics. Instead, it's just a lot of matrix decompositions in algebra, a lot of algebra. And that stuff, I should have brought like a water bottle while recording this. Anyway, algebra. And algebra is like very pleasant to someone who doesn't like infinities, because there's nothing inherently infinite about just symbols moving around, or fractions or stuff like that, or matrix decompositions necessarily. I mean, some matrix decompositions may assume the fundamental theorem of algebra or something, which is not very finite, if you think of it, because it requires the real numbers, or the completeness of the real numbers. But anyway, like, algebra is pretty aesthetic to a finitist, or someone who dislikes infinity, right? And it turns out that in quantum mechanics, we've actually made a lot of progress with just algebra. It's all just algebra, always has been, you know? I think the most beautiful mathematical results are mostly algebraic. So yeah, I think that's the most compelling argument for this philosophy, is that algebra just seems to work. So do algebra, guys. Do finite algebra. Don't do axiom of choice or any of that nonsense. Just do like good old, honest, hardworking algebra. Okay? And it's gonna be hard. Like, if you actually read Professor Waldberger's rational geometry book, some of those things are gonna be kind of annoying. It's like, you're gonna think like, oh, how would you have come up with this? Or like, this is like a lot of work to do all this algebra. But if you do the work, I'd say it pays off, because what you have in the end ultimately is elegant and beautiful mathematics. So yeah, that's what I think. Also about analysis, the reason I think there's hope is that if we consider polynomials with rational coefficients, if you differentiate those, if you like just do the formal operation of whatever the like differentiated polynomial is going to be, well, it's also going to have rational coefficients, and therefore it's still going to work within the rational realm. So like, I think conceivably, like, I don't think derivatives are necessarily going anywhere. We just maybe need to not assume certain things that we currently assume, like the intermediate value theorem and so on. Like, maybe that's just unnecessary additional work that, you know, students have to work through, and maybe that's not philosophically sound, and maybe it's not worth it, you know? I don't know. I mean, for sure, I think anyone who's done actual real analysis, where we go through the whole shebang of going from the completeness of the real numbers to the intermediate value theorem and then to all these other results, you will know that it's a pain in the ass. It's not fun. And maybe it's actually not the way to do it. But that's a strong statement. And I'm not going to say that I definitively know what we all should be working on as mathematicians. I don't know. But I am suggesting that maybe we should all kind of think about these things, you know? Think about the beauty and elegance of models that we understand, right? Because, like, at the end of the day, I strongly do think that a lot of the ambiguity that comes from, like, all these different models of ZFC, for instance, like, there's one model that we just showed that, you know, it happens to, well, we didn't show that it satisfies the continuum hypothesis, but it does. And there might be some other, or there literally is some other model that doesn't satisfy the continuum hypothesis. So there is, like, a certain sense of ambiguity there, right? But there maybe doesn't have to be. Because I think if we consider finite models, then I think the right questions to ask and the right answers to those questions, I think, will come naturally. Like, it's hard for me to conceive of a question regarding a question in a finite setting that would not have a definitive answer. So I think we will solve a lot of the ambiguity that we're currently dealing with if we jump to a more finite setting. And yes, we'll also lose a lot, but I think we'll gain even more. That's what I think. So, yeah, tell me in the comments what you think. And thank you for watching. And, you know, I think after a long math session like this, I mean, you can click off if you think you can click off the video, but, okay, yeah. It's kind of weird, but, like, you know, a little bit of, you know, aftercare almost could be nice. So, yeah, just, we can take 30 seconds to chill. 30 seconds to chill. And ponder the beautiful beauties that mathematics is. It's cool. We can let it all sink in. All the infinity, all the non-infinity, everything. Because I'm not making it to my friend's sauna tonight. And that's okay. I'm chilling. Yeah. I might play some VR chat tonight. Because I opened up this app, so. Or this program, or this game, yeah. Or I might just go to sleep. I don't know. So that was some math. That was a lot of math. I hope you enjoyed it. It would be really nice if, like, now I, like, went into my OBS and, like, turned up, like, the background music to be, like, really audible and it would, like, feel cool and stuff, but I'm not a professional video YouTuber, so too bad you're not getting it. Too bad. But anyway, maybe that's enough aftercare for today, for tonight. So that was it. See you around, and if you'd like to see a VR chat stream, drop a comment, and I'll consider it. Yeah. I have VR, so I might as well play it, because I have not been playing it very much recently. That was it. Alright. Have a great rest of your day or night. Keep mathing on or something. I don't know. It is time. It is time for me to hit the stop recording button now.